All right, so you can see in this review, we're getting back to some things that we've done in the past because they will be coming up in the future for us with different functions like square root functions and cubic functions that we're about to graph. So we're trying to review some other things. So this is a good old quadratic function here, a parabola, right? It's facing upside down. So let's go ahead and do our domain and range. But first, when you do your domain and range, you probably want to label your vertices, and that helps you out. And so there's already a vertice labeled up here, 0.25 and 3.125. Over here, remember this is on the left, so it's negative infinity, and it's going down, so that's also negative infinity. Then on the right side, it's on the right side, so we're on the positive side of the x-axis, and this one's the negative side, right? So we're on the positive side, but we are still going down. Okay, so that infinity right there. All right. So once we have those labeled, then we can go over and then do our domain and range. Remember, our domain is the smallest and the largest x value. So that would be negative infinity to positive infinity. It's the width of the graph. All right, our range is our low to our high. So our lowest is negative infinity, but our highest is right here, this y value here, 3.125. So we want to say negative infinity, comma, 3.125 with a bracket, because it's touching that. Increasing interval. So this left side here is increasing. It has a positive slope to that side. So that's increasing from negative infinity all the way to this x value of 0.25. So let's see, negative infinity to 0.25, always use parentheses. And the other side is decreasing, so from 0.25 on. So from 0.25 on to infinity. Okay. All right, x-intercept. So I already gave you this x-intercept here, 3/2, it's 1.5, because it was right in the middle, so you figured you couldn't really tell exactly where that was, but it is at 1.5, or 3/2. This other x-intercept is at -1, which allows you to write your factors. So 3/2, remember, you're saying that x equals 3/2. So the 2 used to be with the x, so it used to be 2x. And 3 used to be over here, so it used to be 2x minus 3. And that's the factor that we use to solve for that x-intercept. So 2x minus 3. And the other one used to be -1, so x used to be -1. The 1 used to be over here, so it used to be x plus 1. So these are the factors that made these zeros. All right, end behavior. So we've already have our end behavior here. End behavior is the y values behavior as x goes to positive or negative infinity. So they're both pointing down. So as x goes to infinity, so y goes down to negative infinity, this one. And same thing for the negative infinity for the left side. All right, so we have some transformations here. Remember that anything that's a negative in front is going to cause a reflection. So this guy has a reflection over the x-axis, and this -4. This -4 is after the x, it's not with the x in parentheses, so that would be down 4. We're trying to remind you of these transformations and all this other properties up here because we're going to be using those when we talk about graphs of radical functions. All right, so this guy also has a reflection. All right, it moves to the right 3. So remember, it's opposite once inside. Inside is side to side, and it's the opposite action that you might think. So it moves to the right 3. And then the 5 moves you up 5. All right, this guy, no reflection, it moves you left 1 and down 2. These would all be parabolas. These are all quadratic functions because of the x squared in these problems. All right, this 2 in front, remember that's going to be a stretch. Makes your graph like skinnier in a sense than it used to be. And then the +3 moves you to the left 3. And remember, if it was a number like 1/2 or some number below 1 here, right in the front, that would be a shrink. All right, looking at this parabola. So the parabola, the vertex of this parabola is left 2 and down 5. So left 2 and down 5. So if I make that happen, oops, the y equals is already there. So left 2 means I am going to go let's see, I'm going to have x plus 2 squared to make it a parabola, and down 5 minus 5. It's facing right side up, so I don't need a negative. Also need to check one more thing. Parabolas normally follow this pattern. When they go out 1, 1 squared is 1. When they go out 2, 2 squared is 4. Out 3. So if I do 3, I'm sorry, if I go out 3 spaces, then I get 9. So that's a normal pattern for parabola. If you have a parabola that you plug in 1, you get 1, you plug in 2, you get 4, you plug in 3, you get 9. That's a general pattern, and it's following that pattern. So it has not been shrunk or stretched or anything like that. All right. So down here, we're going to solve these two problems in number 4 by factoring. So to factor, we have to put everything together on one side. So I'm going to add 6x here and add 6x there. I'm going to take away 2 at the same time. So I end up with 2x squared plus 11x plus 14. Now remember, you can use Photomath to check your answers, but you don't want to use Photomath to do your work for you, please. So 2, 11, and 14 have nothing in common, so I'm going to set myself up to factor. I got 2x and x. 14, we could try 7 and 2. So I can't put the 2 here, so I'll put 7 here and 2 there and test it out. I'm getting 4x and 7x. Yeah, 4 and 7 make 11. Everything's positive. Okay, and so now when I solve this, 2x plus 7 equal to 0, I would take away 7, divide by 2, I get negative 7 over 2. And I would set x plus 2 equal to 0, take away 2, get x equals negative 2. It says to write them in a solution set. So my answers are negative 7 over 2 and also negative 2. And remember, you can also graph these things in Desmos. If you graph 2x squared plus 11x plus 14 in Desmos, you can kind of confirm what's going on here. And I think I'm going to put y equals just because I like it. You don't need it, but look right there, negative 3.5, negative 2. There's my x-intercepts, which are turned into my factors and everything. Okay. This guy down here, I'm going to take away 15. So I get 5x squared minus 23x minus 10 equals 0. All right, so again, same process, 5x and x. I think I'll use 5 and 2. I can't put the 5 here, so I'll put 5 there and 2 there. This is making me a 25x. This is making me a 2x. So 25 and 2 to make negative 23, I'll need a plus 2 and a negative 25. So that one's a negative, this one's a positive. So my answers, this guy right here is going to be negative 2/5. And this guy right here is going to be positive 5. And again, you could check in Desmos if you need some help on that too. You would set it up the same way here. You'd get negative 2/5. And the other one, you'd get x equals 5. All right, so number 5, graph this parent function. Graph the parent function, absolute value of x. Remember, absolute value, those are your v-shapes. So absolute value of x looks like this. So I will circle that in red so you know that that's the red one. So remember, it starts at 0, up 1 over 1. And you could get this by doing a table if you like. So there's absolute value of x. And also, if you go back 1, the answer is still 1. Back 2, the answer is 2. So it goes up like that. So there's your parent function. And then graph x minus 4, absolute value minus 3. So that's going to move you to the right 4 and move you down 3. Okay. So right 4, down 3. So right 4, down 1, 2, 3. There's my vertex. Up 1 over 1 because there's no change in the slope. No stretch or shrink. And this guy goes right there. Up 1 over 1. And remember, you can also go to Desmos and graph these things if you need some help. You just have to type in ABS. So if you type in, y equals, put ABS, I'm pretty sure. Absolute value, maybe not. Okay, well, never mind. I thought that was in some other program I was using. So anyway, you just get your absolute value bar right there, and then put, x minus 4, and then put another bar, and then minus 3. And you can see the picture. Okay. Also on your keyboard above the enter key, those straight bars. That's what I was thinking of. All right. So on to the last page here, we're going to simplify some of these radicals. So notice this has a 3y out front, so anything that comes out is going to multiply by that. Okay. So let's get to it. 27. So I'll put 27 over here so it won't muck up that space right there. 9 times 3 and 3 times 3. Also, you might know that 27 is a perfect cube. So there's a 3 coming out, because there's 3 3s. So when I have a 3 coming out, there's already a 3 waiting. So 3 times 3 is 9. All right, and then, so that guy's done. 3 goes into 6 twice. So I'll have x2 coming out, no x's left. And 3 goes into 4 once. So notice, this is maybe a little different than some things we've done before. 3 goes into 4 one time, and there's already another y out there. So it means there's going to be 2 y's out there. But left in my cube root, 3 went into 4 one time, and there's still 1 left. So that's still there. So there's your final answer. All right, number 7, a cubic polynomial. So those words right there. Remember, cubic means x to the third. Polynomial, that's when you had, we did last chapter. Remember, that was just like a long problem with a bunch of pluses and minuses with expressions like x to the third and so forth. So anyway, write the factors. So we have 3 zeros. So that means that if I was graphing this thing, it would cross at -3, it would cross at 5, and also 2/3. So, you know, it might look like this. It might come up, go back down, go back up through there, whatever. It doesn't have to look like that, and you don't have to know that right now, but we want to write the factors. So the factors for -3, the factor would be x plus 3, because it's crossing at -3. For 5, it'd be x minus 5. Remember, it's always opposite. And then for 2/3, that would be, remember, we got x equals 2/3, so it'd be 3x, and then minus 2. All right, number 8. We're multiplying and simplifying. So with multiplication, you always want to like multiply it first, just to see what it all amounts to. These are both 4th roots, so that's important. They have to match. So 5 times 4 is 20. I have one big 4th root. And remember, when I multiply, I add my exponents. So 4 times 8 is 32. X and x to the third make x to the 4th. Y squared and nothing there, so it's just y squared. So now we reduce like we did in number 6. All right. So 32, I'm just going to use 4 times 8 like was up there. And I got 2 times 2, and 4 times 2, and another 2 times 2. All right, so when I look at that, I can see that I have a 2, a 2, a 2, and a 2. I have 4 2's. So I'm going to go ahead and bring a 2 out. Now, I'm bringing a 2 out, but there's already a 20 there. So 2 times 20 is going to be 40. Leave some space for my variables. Put my 4th root back. There's this 2 left inside. All right, so that's the worst part. 4 goes into x4 one time, so one group of x's are allowed out. And, I don't know, 4 doesn't go into 2 at all, so the y squared is just sitting there. So it turns out I don't really need that much space, so let me see if I can, I can't drag that over. So anyway, that's your answer. That big space in the middle doesn't need to be there. All right, with division. Remember, just like multiplication, division, you want to divide them first if you can. And these are both square roots, so I can. So I'm going to make another problem. 8 divided by 2 is 4, and that 4 is going to be on the top. All right, so there's going to be a 4 up there in the numerator. I have x and x to the third. So remember, you subtract your exponents. So 1 minus 3 is -2. That means I have x squared on the bottom. And then the y-5th has nothing to do. Okay, so now we just have 2 problems to do. So in the denominator, the square root of x squared is just x. Remember, you have a 2 here. 2 goes into 2 one time. No leftover. Up top, I know the square root of 4 is 2, so I'm going to bring out a 2. But the y is a different thing. I have 2. 2 goes into 5 twice, so it's going to be y squared. And there's going to be a y left inside. So that would be my final answer. Alrighty, so moving on to number 10. In number 10, we're adding and subtracting. Now, adding and subtracting is special. The radicals and what's inside of them, the radicand, have to match. So remember that when you have a radical, this little number right here is called the index. This is called the radical symbol, and then the stuff inside is called the radicand, radicand, and then this is the index. So they have to match to be able to add and subtract. Okay, only the index has to match to be able to multiply or divide. So here we go. So this guy right here, if I look along here, 5 cube root of 2, I see another cube root of 2 over here. So this matches that. I can put those together. 5 plus 3 is 8. So I get 8 cube root of 2. This minus 6 square root of 2, it just sits there. 6 square root of 2. That's it. That's all I can do. All right, this guy right here, 6 radical 5 plus 6 radical 2. I can't do a thing. There's nothing to do, so my answer is still the same. 6 radical 5 plus 6 radical 2. I cannot add those together, unless I'm going to do it on a calculator and get a decimal. For letter C, when I look across there, I got cube root 4, cube root 4. These two are like terms, but cube root 2, nothing. I can't do anything with that. And cube root of 4 can't be reduced. 4 is 2 times 2, so there's not enough numbers to bring anything out. So negative 3 minus 6 is negative 9 cube root of 4, and then plus 3 cube root of 2. That's all you can do. All right, and looking at the bottom, they're all 4th roots of 7, so they all have similar things in the front. So 5 minus 2 is 3, and 3 minus 3 is 0, so that's nice. All right, with number 11, these do not match, and so I need to reduce each of them to see if they will match. So let's take a look. 16 is 8 times 2. 8's a perfect cube, so you might know that you're going to bring a 2 out, but if we break it down, you do see, hopefully, that a 2 is going to come out of that. Got 3 2's. All right, so a 2 comes out. There's already a 2 waiting. So that's 4. X is already there, and I have a cube root of 2 left over. So let's see what this 54 does. So 54 is 9 times 6. 9 is 3 times 3, and 6 is 3 times 2. So hopefully you notice that I have a bunch of 3's coming out. Oopsie. Those 3's right there. So when I bring my 3 out, there's nothing waiting, so it's just going to be a 3. And x goes into, 3 goes into this 3 one time. So 1x is coming out, and when I look at my cube root, there's that 2 left inside there. And there's no x's left because 3 went into 3 perfectly. All right, so let's take a look. They're both cube root of 2. I just need to do one check, make sure that this is the same type of thing as this, if it's a common term, and it is. So 4x minus 3x. Well, 4x minus 3x is 1x. And so usually you don't really write the 1, so I'm just going to put x cube root of 2. And if you really want to write the 1 right here, go ahead. All right, last few problems. Number 12. 12 says to write each expression using a radical instead of a rational exponent. So a rational exponent, remember, is a fraction. Right, so we're going to use a radical, and we're going to simplify it if we can. So 16 to the 1/4. So remember, that means the 4th root of 16. And so there is a 4th root of 16 of 2, because 2 to the 4th is 16. All right, this one means the cube root of 3x, and I can't do anything with that. 3 can't be broken down. There's not enough x's, so that's finished. This one right here means the square root of 18 xy, right? Because remember, 1/2 means square root, so 4th root, cube root, square root. All right, and so 18 can be broken down. 18 is 9 times 2, and the 9 is double 3's. So we're going to bring out a 3 and leave in a 2. So bring out a 3, and then leave in a 2, and the xy haven't been touched. All right, with number 13, we're going to do the opposite. These are radical expressions, and we are going to put them in exponent form. We're going to put that with rational exponents. All right, so remember, power over root. So this is x to the 3/4. And 3/4 doesn't do anything. It doesn't reduce. So here we go. Remember, this is a square root. This 4 has a 1 on it. So 4 to the 1/2. X to the 6/2. Y to the 7/2. All right? So I need to reduce this. 4 to the 1/2. I do know the square root of 4 is 2. 6 over 2 makes 3. And then y, 7 over 2, would just stay the same. Okay. This next one, this 27 has a 1. So I could go ahead and do that right now. I mean, I know the cube root of 27 is 3. So you could do it like this, or you could just literally write 3 right now, all right, instead of having to do it later. Or you could write it like we did up here. You could write 27 to the 1/3. This would be x to the 5/3, y to the 6/3. Well, I know 6/3 turns into 2, right? And then the last one, z to the 12/3. Well, I know that 12 divided by 3 is 4. So if you want to just do it as you go, it makes it a little faster for you. All right, number 14. We are going to simplify this using our exponent rules. So we could also do number 14 kind of like we did here, but let's use our exponent rules. So 49 gets a power of 1/2. Remember, when we do our exponent rules, we multiply exponents when we have an exponent on an exponent. So I get x to the 6 times a half. Half of 6 is 3. And then 8 times a half, well, half of 8 is 4. Okay, and then I know that square root of 49 is 7, so I should further answer 7x3 by 4. Right, and then number 15, everything has a negative exponent here, so why don't we do this? Let's see. There's a couple of different ways to do this. I could go ahead and give this negative exponent to everything, so I'll do it one way. This would be 5 to the negative 2, x to the, remember, 2 times negative 2 is negative 4, and this would be turned into positive 6. So when I'm done, what I would do is I would put these guys on the bottom. So I would put 5 squared on the bottom, x to the 4th on the bottom, and leave y to the 6th up top. So when I'm done, I would get y to the 6th over 25x to the 4th. Another route you could take is this. You could say to yourself, I could fix everything inside here. You know what? I'm going to stop right there and say that the way that I just did it is probably the least confusing way to do it. So let me just stop you right there and leave it at that. Because there are other ways to do it, but that was probably the best way to do it. All right, so the last problem, 16, we're going to do the same thing. 4 to the 3rd power. We're going to evaluate that later. X, 6 times 3 is 18. And my y, negative 2 times 3 is negative 6. So when I'm done, 4 to the 3rd is 64. 4 times 4 times 4. So that's going to turn into 64. The x to the 18th doesn't go anywhere, but the y to the negative 6 goes to the denominator. So you always want to have positive exponents when you're done, so put everything in their place. All right, that is it. See you in class. Bye-bye.